In this video, we're going to talk about arc length and learn probably the easiest formula of the year. If you look at this diagram that we have on screen, you can see the arc length marked off in red. That's the arc that we're talking about. An arc is a section of a circle. And I have it measured, but I don't know where that number came from. You can see that as I kind of rotate this around, all of the angle changes, the arc length changes. I can change the size of the circle also, and the circumference, radius, arc length, they're all going to change. But there's no rhyme or reason that I can see there. Unless, if I don't just measure the different individual measurements, but if I start comparing them, I will see a very clear pattern. So first off, I will calculate the ratio. That's what we're going to look at here. The ratio of the arc length, which is just that red length from A to B, which I couldn't measure with a ruler or anything because it's curved, divided by the entire circumference. I don't really care what that number is right now. But if I were to compare it to another ratio, the comparison between the angle that makes the arc, the size of this angle in here, compare that to a 360-degree angle, because that is the measurement of an angle that goes all the way around, and you can start to see that even though those numbers, I don't really care about the 0.16, that doesn't mean anything to me, but notice how it's the same in both fractions. Both comparisons, both ratios are equal to the same. No matter how big that circle gets, no matter how big the angle gets, notice how, as everything moves around, the comparison of the two are always equal to each other. Of course, that decimal keeps changing, but those two fractions are always equal to each other. In other words, put that as a sentence, the ratio of the arc length over the circumference and the ratio of the angle over 360 degrees always match. And so we can write that as an equation. Arc length over circumference equals the angle, which we can actually call the central angle, over 360 degrees. And you might be thinking, well, we don't usually put whole words into equations. And you're right, so let's fix that. We don't need to use the word circumference because we have a formula for what circumference equals. Circumference is equal to 2 pi r. And arc length, I can give it a name too. I honestly could not tell you why, but the name we give arc length is S, capital S. I really don't know why. Equals the angle measure. Well, we have a variable we usually use for angle. We usually use the letter theta. And 360 degrees, well, that's already nice and simple. So S over 2 pi r equals theta over 360 degrees. Now, this still sounds a little bit complicated, but I promise we're going to make it easier. And this is one place where you see why radians are so wonderful. This is currently in degrees. We measured our angle in degrees. We're comparing it to 360 degrees, but I'd rather that be in radians. So what I'm going to do is make a conversion here. I'm going to convert from radians to degrees, but it's going to be a little bit different from how I usually convert it, because what I really want to cancel out is this degree symbol. So I'm going to multiply by 180 degrees over pi. I know normally when we convert from radians to degrees, from degrees to radians, we multiply by pi over 180 degrees. But this is a little bit different because the degree symbol that I want to cancel out is in the denominator. Well, if we do this multiplication, the degree symbols cancel out. And I have S over 2 pi r equals theta, which is now in radians because we've made that conversion. And the 180 over 360 reduces to 2 in the denominator. So s over 2 pi r equals theta over 2 pi. But those 2 pi's can cancel. If I multiply both sides by 2 pi over 2 pi, sorry, I don't need to multiply by 2 pi over 2 pi because I'm multiplying both sides. So if I multiply both sides by 2 pi, then now my equation is s over r equals theta. And then if I multiply both sides by r, I have a formula that has s by itself, s equals r theta. And that is a formula for arc length. As long as this theta is in radians. And so this is one reason why radians are so great, because when we have an angle given to us in radians, we can talk about the arc length very, very, very easily. And so that's our big formula for today, s equals r theta. I promised it was going to be easy. And we can see how easy it is to use also. So here a circle has a radius of 6. What is the arc length of an arc with a central angle of 2/3 pi radians? Notice how that is not the circle I have drawn there. The circle I have drawn there is just to highlight what the s, the r, and the theta are. It does not fit the diagram. That diagram does not fit problem number 1. So let's draw a circle with a radius of 6 and a central angle of 2/3 pi, which by now we should be pretty good at placing that at 2/3 of a semicircle, somewhere in the second quadrant there. We want to know, what is this arc length? Well, this is just applying the formula. S equals 2/3 pi times r. And 2/3 of 6 is equal to 4. So the arc length is equal to 4 pi. There were no units of measure given here, so I don't really have anything to put. And that's my answer. Notice how when I've answered my question for s, there's often still going to be a pi in my answer. That doesn't mean my answer is an angle. I stressed this a lot last week. Pi does not mean angle, it does not mean radians. It's just a number. A little bit more than 3. So this arc length is 4 times a little bit more than 3, or something more than 12. It ends up being about 12.5 something. If we were measuring, if I would have given you a units of measure here, like centimeters, then that would have been the units of measure of my answer, 4 pi centimeters. Make sure you're very careful about units here. Use whatever information they give you. So for number 2, a monster truck has a tire radius of 33 inches. 33 inches. How far does the truck travel in 2/3 of a tire rotation? So 2/3 of a tire rotation, that means that it's spinning around 2/3 of the entire circle, not of a semicircle. So it's not, the angle here is not 2/3 pi. The angle is 2/3 of 2 pi, because that's the full rotation. 2 pi is the full rotation, so 2/3 of that is this angle. 2/3 of 2 pi is 4/3 pi radian. So it's a little bit weird to talk about the distance traveled as the same thing as the distance around the outside of the arc, but that's what happens when a wheel drives. However far whatever the length of this arc is, that's how much ground is covered, because it's as the wheel turns, the monster truck will move forward by that much distance. So whatever that distance is the distance that the truck travels. So we can again use the s equals r theta, 33 times 4/3 pi. And again, notice that we'll have a pi in our answer for length, which, yeah, that's a little bit weird, but that happens a lot. The 33 over 3 we can reduce to 11, so 44 pi inches. And the last example we'll see here, if a circle has a radius of 8 centimeters, So we'll put a circle here with a radius of 8. How big of a central angle is needed to make an arc with a length of 16 centimeters? So I want an arc around here that is 16 centimeters long. How far around do I need to travel to make that happen? This is a tiny bit different because we're not given the r theta just to multiply together to find s, but it's not that much trickier. We're given the s is 16. So if I take the formula s equals r theta, we're being told the s is 16. We already know the r is 8 centimeters. And so what we want to know is, what does theta have to be? And so we're just solving for theta here. It is 2. It is very important to think about 2 what, though? It's not 2 degrees. It's not 2 pi. It is 2 radians. That is the size of that angle. Remember, 3 radians is a little bit less than a semicircle, because the semicircle is 3.14 radians. So 2 radians is a little bit less than 2/3 of a semicircle. So that angle is a little bit less than 2/3 pi.